All right, cool. You have a chance to take a breath and enjoy Wednesday. Have a whole morning off, right? At least like 50 minutes, some time. Or did you take the time to like speed through the rest of the problems? It's okay. Yeah, it's good to like take a break and just acknowledge like I'm working hard. I deserve this. I'll go get a coffee instead. All right, so speed run of kind of where we're at. Dealing with like multiple moving parts like this, it is kind of a long process, at least like going through the stuff. Like at the end of the day, we'll end up with like equations that we can solve, but getting there, that's the hard engineering work. Then you can always like pass it off to somebody else. Like, got these equations that are unsolvable, and that's like, no, you don't. We can solve them. Like, give them to me. So we have this 4-bar linkage. We know like where it is currently, and we know how fast one of the parts is moving. We want to figure out how fast everything else is moving. And what was this like when we created those like vector equations? Why were we doing that? What is that giving us? Do you remember? I know I'm asking you to think back to like Monday, and it's already Friday, and you can smell the hot wings already, like at the end of the week or something. I don't know what the end of the week. Maybe just Dunkin' Donuts and but something like the end of the week reward. But what was the goal? Because we end up with like these equations. Why are we even trying to do that? What is that telling you? Or telling us, like, as we're kind of doing this together? Yeah. Yes, we can like components.
We're just trying to like predict the motion of the whole system because we know it's 4 degree freedom. Okay. Just predict the whole system because it will eventually like independent variable.
All right. Yeah. So what are those equations? It's only one variable. Why are we all using equations?
Well, I don't know like where we're gonna go.
Okay. Yeah.
It's like really.
Yeah. So we know theta 1 dot with our crane bar is moving always 10 radians per second in a circle. We're trying to figure out like when this thing is in this orientation, how fast is theta 3 changing, how fast is theta 2 changing. Yeah. Okay, some relation between them. There's probably a reason, yeah. Probably a good one. Hopefully a good one, right? I don't like wake up every day and think like, what's a new trig problem that I could do today? Like it keeps coming up because there's a lot of trig in engineering, but it's not, my goal is not finding new ways to apply trig. My goal is, here's an engineering problem. How do I turn it into an actual problem that I can solve. So when we were first looking at this kind of big picture, we figured out 1 degree of freedom. Like there's only one, if one thing changes, the whole system changes. So one way you could think about that is like you only need one motor for this. And if you have one motor controlling L1, like to spin L1, the whole thing is going to follow. So 1 degree of freedom, one source of motion. L1, L2, L3, and then that kind of the base L4, those are all like constant values. They're not going to change whether the system is moving or not. Like they have to make some kind of quadrilateral thing. So then really there's like 3 things that we care about: a theta 1, a theta 2, and a theta 3, if we think of it as like what coordinates define this quadrilateral. It's theta 1, 2, and 3. So there are 3 things that we need to know like what it looks like, but we know that only one of, if we change one, the other 2 have to change. So what we did here is we created 2 constraint equations. 3 minus 2 is 1. So if we know 1, we know 2. We know the other 2. And that's what this step is doing, like big picture. If you have 9 degrees of freedom, and you know there are like 9 things to describe like where this thing is, like if all 4 of these things were like moving, but we know there's 1 degree of freedom total, I need 8 math constraints on this thing. So some of the math constraints were kind of like, okay, L1 is constant. Like we know that, cool. So O to A is always a given value. But then now we have a relation between theta 1, 2, and 3 with 2 equations. Kind of makes sense? So yeah. And some people were kind of thinking of this of like, well, helps to describe things with vectors, because like that's the whole process of kinematics. But here we're like thinking about kinematic constraints, like how is motion constrained. Anyway, so we got this. Once we have constraint on position, we have a constraint on velocity. So we ended up with like all the Vx terms have to add up and they have to be equal to each other, and all the Vy terms have to add up and they have to be equal to each other. So what's next? How do we solve it? And we just need to like plug in values, right? We have 2 equations with 2 unknowns. At least we should have 2 unknowns. How many unknowns do you see? 5? No. 4? Maybe 4? 5? Maybe 5? All the derivatives? Okay. All right, so let's grab. Oh yeah, we started writing this out. And then I gotta grab this guy, just so we can start plugging things in. And then I know I'm trying to like organize it so it's all in one place. So let me plug in the stuff that I know right off the bat. I know L1 and I know theta 1 dot. So here's L1 and here's theta 1 dot. So 10 times 2 times 0.25, 2.5 meter per second. Yeah, thanks. I was just, yeah. I deleted it and then copied it incorrectly. What about sine theta 1? What is that? Do we know what that one is? We know like where everything is. What do we think for like the value of sine of theta 1? Sine theta is opposite over hypotenuse. What's the hypotenuse for our?
Sine theta 1, like the hypotenuse is AC, and that's also the opposite.
Oh, but theta 1 is going to describe like where link 1 is. So right now it's kind of, I don't know, 100 more. It's more than 90. So maybe 110 or something. I don't know. So what's the hypotenuse for sine theta 1? Like opposite over hypotenuse. How big is link 1? Kind of like if I'm making a right triangle out of this whole thing. I can say that it's something over L1 because the triangle is L1 hypotenuse. Maybe? No? Different approach? Thinking about it. I'm going to write up what I think and tell me what you think. That's what I think.
The numbers, it looks like it would be right.
Okay.
But you know it's not as small as L1 is, which is 0.25 meters.
Okay. Yep.
The 0.1459, that's still a 5 component of the height of A.
Yeah.
But beta, that's like the angle complementary, supplementary to beta.
Would that be sine
Yeah.
180 minus theta? Is 1.59 L1?
It would be the value of sine theta is still going to be the same, even if you say 180 minus it.
Oh, yeah.
Yeah. So at least if we're trying to find like the actual sine theta and keep that the sine, all we care about is the sine, like
So if you did 180 minus the angle and still did the trig functions, it'd be the same.
Yeah, not always, but
Yeah, because it's above the x-axis.
so right now we're over here in like we're somewhere up in the positive, or wait, we're in the more than 90, right? Like somewhere over there. So I think even if we subtracted, then end up like over there. Is that right? Yeah, subtract pi and end up on the other side of, so the actual value of sine wouldn't change even if we'd said subtract 180 from it. All right, so if that's sine theta, cosine theta 1 still over L1, what's that numerator? What's the adjacent part?
Yeah. Yeah. And we know like where it is. We know where our A is. Yeah. X and Y components. Yeah. Yeah, like in that where it says R A equals -1, 2, 5 plus 0.1. So that's where I got like 0.15. So we go back there. Yeah. Theta 1 is like if theta 1 is 0, then L1 is pointed at C. Yeah, I know there's so many arrows on there. Yeah, small. That's where it's about that yeah, the horizontal, the axis is negative. Yeah.
So I'm grabbing like the I and j components of A to describe the sine and cosine here, because I know where it is in the sense of like putting in Cartesian coordinate there. I'm now, instead of finding the angle and then plugging the angle back into sine and cosine, And just say like, all right, here's opposite, here's the hypotenuse, adjacent, hypotenuse. Nice way. Save a little bit of back and forth, right? I'm just gonna write 1.5. All right, what about sine theta 3 cosine theta 3? Because that's like our next step, right? And I'm just writing out some of the stuff that we know. Give myself a little more room. I'm going to use 1 sig fig just. So I know like position of point B up here. And I just wrote like what components I know about how to get to B. Sorry, yeah.
The second term in J, so next to the 2.5, is supposed to be, I think we probably repeated it twice. Like the 0.15 and 0.25, isn't it supposed to be like 2, 3?
Yeah, probably. Yeah, the cosine should be a negative 0.2. Thanks. Yeah, because the adjacent part is over in quadrant 2, so like negative 0.2. All right, now we need sine theta 3. Oh, I don't know why I wrote theta twice. And the main part that we need is the opposite and opposite and adjacent. Yeah, because we're always creating like a right triangle with the links themselves.
And then because sine, the opposite, the J.
Yeah.
So the J can run over L, and I can run over L.
Yeah. Okay, yeah. But if I take like sine of the angle, All right, we tried it out. So that opposite part is describing from, oh yeah, let me write in this. From C to get to B, the sine component of that is going to be I go up L3 and the total like vertical distance that I traveled was that 0.86. So then going along the horizontal like x-axis for that cosine component, I'm still doing that L3, but now I'm saying that it's 0.494. I wrote out 0.5 minus 1. Because really I'm taking like that relative position of C to B, right? Or like B with respect to C. Kind of see where that's going. This is, so like with dynamics, sometimes it's easy to get lost in the weeds of like all this math and trig and trying to wrap your head around it. But main thing is like, if we know what the positions are, then we should know what the angles are. And sometimes we might get a little confused about like where to put what, but we roughly know what these angles should be. Something like that. Just remove those the L3s, and plug in the values of like the actual X and Y relative positions. What was that? Negative 0.2. And this one is 0.14. Now you're experts of all these relative positions and stuff. So what do we think that next sine theta to cosine theta to?
It's a nice, like, consistent, like, tracking angle beyond. If it's 0, you could define the angle differently. Yeah. Okay. Yeah, I don't know. Your right is like vector RE vector. Sorry, yeah, vector B, vector A, because I know orientation of. Yep. What do you think? What's that sign? Oh, yeah, yeah. Okay. Then where's that theta 2 just now? Yeah. kind of makes sense to do like how long and X equals A, B. Yeah, like if you did this,
How did it go? Experts at trig now? Take the step up to B, subtract that step up to A. Now I have the relative step B with respect to A. Cool? No issues? And now take the step 0.5 out to B, subtract that negative 0.2 to get to A, and I have 0.5 plus 0.2 to get from B with respect to A. Cool. And now I can start deleting stuff in here and call this plug in all those values. Now we finally have an actual two equations with two unknowns. The general process for this is like solve the constraint equations for position and then solve constraint equations for velocity, because usually velocity is also a function of position, where the thing is. Cool. And let's grab that, paste it down here. How do you solve two equations, two unknowns? What's your preferred method? Substitute? Oh, so you're like a system of equations solver? Okay. System of equations solver? Okay, that's fine. No one's like, I love linear algebra. No linear algebra takers? No? Later? Yeah, someone else's problem. This one is a linear algebra problem, because like theta 3 dot and theta 2 dot are two unknowns. So really it's like a 2 by 2 matrix, so, and then some right-hand side vector like that. But however you want to do it, try it out. Two equations, two unknowns. You can use substitution. If you like systems of equations in your calculator, this will work great because it's all linear, but however we want to do it. You can guess and check. That's actually a pretty solid way to do things. But remember, two equations, two unknowns.
One of the values of
that one was like you could use negative 0.5, but really it's like 0.494, right?
yeah, I'm just trying to remember.
So to get the relative like B with respect to C, go over 0.494, subtract that 1, so you end up with a negative 5
Yeah,
or 6.
I was trying to see why I put 863 there.
That is probably transcription, just as you copying it from one to the next. Put in your own calculator actually. Solve. Don't build out the answers. Doing styles,
Like, it got better and like sort of watching.
She just happened. Like you don't connect with her.
Oh, because it cancels out.
yeah, I would just put
Yeah,
a
yeah,
shortcut of
okay.
like since it's L2,
Yeah,
something
got
over
it.
L2.
These just cancel.
Yeah, so then just ends up being
Yep.
blank.
Yeah,
Sometimes it just hurts. Yeah.
Which class? Dynamics. Um, all right, so do you want to see like a Python two equation, two unknown process, like how to set it up? Or Python? Yes, no? What? Yeah.
Are you solving for theta 2 theta 3 on Python, or are you plotting?
I was just going to solve for this one case. In the project, we'll like solve for as a function of time, like what's happening. Do you want to do it in Python, or is that like totally useless?
We use like a online thing. I don't know if it looks like Python, and we would set up the matrix and then
Yeah.
reduce it, and it gives us.
Yeah, so you can either set it up as like, hey, solve this matrix for me, or you can set it up as a series of equations and say solve these equations. So either way, which one do we want to do? Equations? Equations? All right. So I'll say like my equations, I'll call them so main thing is that we want to create two equations that equal 0. Like if you're trying to solve a system of equations, it's easy to find 0. It's very hard to figure out when one thing equals another. So numerics, it's better to say like set the whole thing equal to 0. So I'm going to say 2.5 times 0.15 over 0.25. I need some more room too. Minus x0 times 0.86 plus x1, or actually I want to switch it. I want to call this x0 so that x2 is x1, and then times 0.86 minus 0.15 and then 2.5 times 0. I'm going to put a negative there. 0.2, 0.25 minus x bracket 1 times, I guess it'll be a plus 0.51. And then plus x bracket 0 times 0.5 plus 0.2 and then I also want to say from scipy.optimize and I think, oh yeah, and whenever you're telling fsolve to solve like a system of equations, right now I'm saying like there is an x is theta 1 and theta 2, so theta 2 is x0, theta 3 dot, the theta 2 dot and theta 3 dot, x0, x1. So I need to give it some initial guess. So I'll just say like 1 and 2. And it doesn't really matter what initial guess I use because it's going to converge pretty easily. And let's see. Yep, there we go. So the values that I get are kind of like 2.5. So x2 is changing 1 radian per second. x3 is 2.6 radians per second. So my rocker is moving this way, 2.5 radians per second. My connector arm is moving up 1 radian per second. What did you get? I saw different values when I was walking around. Did I type in my equations right? Maybe. I might have done it wrong. I have 0.15, 0.25. No, I mean, it could be that I did it. Something wrong. 0.2, 0.25. 0.5, 0.51. I think I did it right. You got the same one? Yeah. Anyway, if you're interested, that's kind of like the process for setting up system of equations. And this one will work even for nonlinear equations. So it'll work however.
So yours is right, right?
I think it's right. I don't know. It seemed we at least have one. We have one confirmation that this was it, but we also had 2 different values. So double check. Usually it's a sign error somewhere in there, like a -1 or a negative. Should have been negative. Something's positive. Well, that's what I get.
Wait, which one's theta 1, which one's theta 3? Or theta 2 and 3?
So the way I plugged it in was this is theta 3,
Okay.
and then this one is theta 2 dot.
Okay, so theta 2.
Yeah. Kind of like that. At least that's the way I set it up. I could have made a mistake. You should check it, but I think it looks right.
Oops. Like